Hello. So far we've looked at some schemes, the simple schemes for numerically solving the advection equation, and we realized that both the forward and the central difference schemes in space are unstable, and so we turn to the upwind scheme, which is the backward scheme, and that's what we want to discuss next, and then we'll move on to the CFL condition and other things. Okay. So here is the upwind scheme. It's backward in space. We can compute the amplification factor, right? If you follow the similar procedures as before, you see that for the case C, for C equals greater than 0, the amplification factor is given by this, right? Where mu is equal to C delta T over delta X. Okay, so again, I forgot to set my time. Let me do that now. So here's the amplification factor. Now we can follow a similar procedure as before and plot the amplification factor. So we can plot the case where the unit circle, and then we'll realize that if the CFL condition is satisfied like this, then the scheme is stable. All right, and we'll see that shortly. Okay, so this is the CFL condition that mu has to be less than or equal to 0. Of course, mu is positive. Well, if mu is 0, this is equal to 1, so that satisfies the condition for stability. We'll see that if mu is less than or equal to 1, that is also true. Okay, so so the graphical approach. So again, we have the region inside a big circle that is a unit circle. For mu equals 0.5, you realize that this smaller circle lies inside the bigger circle that is the region of stability, which shows that when mu is 0.5, the scheme is stable. You can also do the same thing, plot it for 0.7, and you realize that again the amplification factor, the region for the amplification factor lies within the unit circle. So it's safe to conclude that the scheme will be stable. The what is it called? The upwind scheme will be stable. All right. We can draw these conclusions algebraically as well, not just graphically. And so we can take the amplification factor, which is this, and expand it. This is a complex, right? You can write this as cosine of beta, I sine beta, right? So you can expand this, and then you get this. Okay, the absolute value of this squared will be the real part squared plus the complex part squared, which is this. And then of course you can expand this and then combine terms, and then you end up with this. This is easy algebraic stuff, so you can go through it. So lambda, absolute value of lambda squared is equal to this term here. Now we can write 1 minus cosine of theta to be equal to 2 sine squared beta over 2. All right, so you stick this inside here and you get lambda, absolute value of lambda squared is equal to this term here. Again, remember that stability holds if the absolute value of lambda is less than or equal to 1. So that's what we are looking for. So if this guy is less than or equal to 1, then we can manipulate and get a resulting expression. If it's less than or equal to 1, then of course you can also show from the right hand side that mu into 1 minus mu sine squared beta up to 2 beta over 2 has to be greater than or equal to 0. Okay. Good. Now we know that this is a positive quantity. It has to be greater or equal to 0. This is greater or equal to 0. So those are fine. The only thing that can change this sign here is this quantity 1 minus mu. Okay. So which means we need 1 minus mu to be greater than or equal to 0 for this inequality to hold. All right. So 1 minus mu greater or equal to 0 result in the condition that mu has to be less than or equal to 1. So for stability of this of the upwind scheme, require this as before. Okay, so mu has to be less than or equal to 1. So that is what you get if you do the graphical approach as well. You can test different values of mu all the way to mu equals 1. You're going to get this circle line inside the circle of stability. Okay, so these are the two different approaches that we've used: the graphical approach here, and then the algebraic approach, which also shows the same thing. All right. So it tells us the Upwind scheme is stable. Now, physically speaking, why is the Upwind scheme stable? We'll get more into this later on mathematically using the CFL condition. But why is it more stable than the previous simple schemes that we looked at, the forward and the central schemes? Well, if you look at the case where C is greater than 0, for instance, now for the forward scheme, you have a signal that is moving from left to right, all right? And then what you are doing is that in order to approximate what is here, you are using this the values at j and the values at j plus 1 right here. But because this is moving from here, obviously it's possible that the signal hasn't even got here yet, and yet you are using the values here in order to help you approximate what is here in the next time level. So of course it's not going to work. This is just, you know, a hand-wavy understanding of why the forward scheme will not work. Later on we'll look at a more rigorous mathematical approach using the CFL condition. The same way, the central scheme, you are using information from here and the information from there. And again, the signal is coming from here, so good, you have information from here, you have information here, but you may not have information there, and yet you are trying to use that to also approximate what is happening in the next time level there. So physically speaking, that is probably why this scheme will not work. Okay, you can look at the opposite case here. But for the Upwind scheme, you're using information coming from here, so you know you have the history, you have previous information, your information when it gets to j, and so you can use the information here and the information before, because it's a propagating signal, and then to help you approximate or obtain the information in the next time level using what you know. Okay, so this is just a way of explaining that. Good. So here's an exercise you can try. You can write the Upwind scheme for the case where C is less than or equal to 0, and then you can also try to carry out a stability analysis as we've just done for the case where C is greater than 0, and state the CFL condition in that case. Okay, so that's something you could try. Good. So in the next few lectures, we'll look at the CFL condition. It plays a very important role in hyperbolic equations, all right? And we'll use the advection equation to talk about it. Okay, so it's critical. So in the next lecture, we'll go deeply into this, and that will help us to explain this better, right? Why the Upwind scheme seems to work. Okay, because when it satisfies the CFL condition. Okay, so I'll end this lecture and then we'll move on straight to the CFL condition in our next lecture.